everyone, and welcome to the Joy of Abstraction book club, chapter 18, which is about products and co-products. Thank you all for being here. Thank you to the Topos Institute for hosting this book club and for sorting it out. I'm quite excited and also slightly daunted because there are so many detailed questions this time on this chapter. So I'm really glad that so many people are really sinking their teeth in, and I'm feeling quite daunted because there are so many questions. I think there are 28 questions. So this might take a while, but I'm reminding myself that if I need a break in the middle of this video, I'll just take a break in the middle of the video. So let us start with, is the universal laptop charger example from the chapter 16 video, is that an example of a product? If so, could you explain what the morphisms and the vertex are? So I think that the universal laptop charger is an initial object, because I think that it is a cable such that given any cable given any laptop cable, you can plug in an extra tip to turn your cable into that cable. And so there I'm thinking of the cables as the objects and ways of transforming one cable into another as a morphism. Now, it turns out that an initial object is a product over zero objects. And so all we are doing in this chapter is binary products. Let me get the whiteboard up. So in this chapter, we're really doing binary products where we have an object A and another object B, and what we're looking for is a vertex and a projection to each of those. So if we had a nullary product, well, what would that be? So in this situation, I've just realized that it's a terminal object, that's a product. It's the initial object is a coproduct. So anyway, I'll plow on. The nullary product is a product over zero objects. So there are no objects here, but we still have a vertex. And I didn't quite leave myself enough space over here, but look, I can, not like that. I can move this down. Perhaps, can I move it down? So in the binary product, you have a vertex V over your two objects. And then the universal property says, given any X and morphisms like this, you get a unique factorisation, making everything commute. So if you're a nullary product, you have a vertex V, and you have a morphism to every object that you're thinking about. And because we're not thinking about any objects, there's just nothing there. And then the universal property says, given any object together with morphisms to all of our objects, and there aren't any objects, so again, there's nothing there, you get a unique morphism like that. So this is a terminal object. And then a nullary coproduct is the other way around, it's the dual, is an initial object. So I would say that the universal laptop charger is an initial object and thus a nullary coproduct. Of course, dually, that means it's a terminal object in the dual category, but I would rather just call it an initial object. Okay, so the next question, I should really mark off which questions I've done because there are so many questions. Can composition itself be thought of as a product? If the objects are morphisms and a product has two arrows, then the arrows have to be some part of decomposition. So composition is actually a pullback, and that will come up in the chapter on pullbacks and pushouts. And so the idea is that if you have your category C expressed as a set of arrows and a set of objects with a source and target map, then you might think that composition goes from pairs of arrows, right? So it goes from C1 cross C1 to C1, but it doesn't go from any old pairs of arrows, right? So this product would just be any pair of arrows. So you could have an arrow F from A to B, and you could have an arrow G from C to D. And that's not what we want, because we want them to be composable. So we only want to take pairs of arrows A to B and B to C. So there's a condition about these things meeting in the middle. And that's what a pullback will do for us. So a pullback will be a form of a kind of restricted form of product where something has to meet. So that is the answer to that question. If coproduct corresponds to addition and product corresponds to multiplication, would anything correspond to exponentiation? Great question. So exponentiation, there are sort of two different ways to think about exponentiation, and they turn out to be the same in the most restricted context, but then they diverge in more general situations. And so when we're thinking about numbers, for numbers, exponentials, so a, b to the power of a in numbers is b times b times b, a times. And so you can think of it as repeated multiplication. But that is something that really only works if A is a number. And when we're trying to generalize to more situations, we try to generalize to situations where both A and B can be anything. And this is one of the criticisms of the idea that multiplication is repeated addition. So if you define multiplication to be repeated addition, that's fine if you're doing things like 2 times 3, which is 2 plus 2 plus 2. But then if you're trying to do something like 2 times 3.5, then, well, 2.5 times 3.5, how do you repeat something half a number of times? So then that's where we start wanting to have a more general definition. And so another way you can think of exponentiation is to think of numbers as decategorified sets. And so what that means, usually we think of categorifying meaning going up dimensions, but decategorifying can mean going down dimensions and treating things as the same when they were isomorphic. So a number should really be thought of as a set of things with that number of elements. And so if we write for any sets A and B, and we write A for the number of elements of A, then we can do arithmetic by taking products and coproducts of sets. So the number of elements of A coproduct B is the number of elements of A plus the number of elements of B. And we can sort of use that. That's how we define addition, really, when we're teaching it to children. We go, well, if you take 4 objects and you take 2 objects, that makes 6 objects, and you show it to them in front of them. And what you've done is you've taken a coproduct of these 4, the set of these 4 objects and these 2 objects. So then similarly, if you take the product, the number of elements in the product is the number of elements of A multiplied by the number of elements of B. And this is a way that you can define multiplication for arithmetic in set theory. So then, for exponentiation, it's the number of functions from A to B. So you can take the set of all functions from A to B, and the number of functions that are possible from A to B is, well, you take the number of elements of B and you raise it to the power of the number of elements of A. Because for every element of A, you have to pick an image in B. And so you get B number of possibilities for the first element of A, B number of possibilities for the second element of A, and B number of possibilities for each element of A. So it's the size of B raised to the power of the size of A. And so from there, you go, well, this is another approach to exponentiation. So we've got two things. We've got repeated multiplication and we've got function spaces. And so both of these things can be generalized into a notion of exponentiation for categories. It's just that this one is more restrictive. So what we're really doing here is we're taking a repeated product. So this is the product over all the elements of A of the set B. And this only works, so this is A has to be a set, and B can be inside any category. Now, what does this mean? Does this exist? Can this be done? So if this construction can be done for A being a set and B being a object of the category C, then this is called a power, right? Because we're raising the object B to the power of A. But so if C is the category of sets, then it's like doing an exponential because they're both inside the category of sets. Whereas this one, the function spaces, what we're saying is, it's kind of like saying, is there a space of morphisms from A to B? And so in general, if A and B are both objects of a category C, then the space of morphisms from A to B is usually in set, not an object of C. So if you can somehow express morphisms from B to A as an object of C, then that's called the exponential. And so this exponential is an object of C satisfying a universal property. And if this is too much for you, then ignore it, but I'll just, for completeness, say what the universal property is basically. So basically, the idea is that if you have, let me think about this for a second. If you have a morphism from X into this function space type thing, that should be the same as a morphism from X cross A into B. Because a function from X to a function, if you just think of this as functions, a function from X to functions from B to A, what that's saying is that for every element X, you get a function that goes from B to A. So for every element of X and every element of B, it produces an element of A. So that's the same as a product of a function from the product X cross A to B. Let me just think about the next thing I'm going to say for a second. Yeah, I think that's all I'm going to say about that for now. So the thing to take away from this is that there are two different approaches to exponentials in a category, depending on whether you're generalizing from repeated multiplication or from function spaces. Good question. Okay, let me move this up. And we will move on to the next question. Is modeling ability a standard characteristic of a universal property? If so, what could you use products to model? I'm afraid that my psychic powers are failing me on this occasion, and I'm really not sure what you mean by modeling ability. Is a modeling ability a standard characteristic of a universal property? What could you use products to model? Well, I suppose what you're modeling is you're taking some diagram in your category, and you're kind of modeling that diagram with a single object. Because what you're saying is, can I replace the information? Okay, here's an answer. Category theory is about relationships. And so if you have a whole diagram of stuff down here, and you've got some single object up here and it's relating itself to this diagram, maybe you want to model that diagram by a single object here, so that instead of X having to think about how it relates to the whole diagram, you can just think about how it relates to this object here. And so that's what a product is doing, where the diagram happens to be just a pair of objects. And so when X is trying to relate itself to this pair of objects, it will have to keep doing so by a pair of morphisms. It might go, oh, this is so arduous. Why do I have to use two morphisms all the time? So instead, you can model the situation with a single object here, which happens to be equipped with projection morphisms that deal with the pair situation all the time. And then you can model the entire interaction by a single morphism like this instead of two. So perhaps that answers the question a little bit. Okay. Right. I'm already quite tired, and there are 24 more questions. Good heavens, well done, everybody. So I think what I'm going to do is I'm going to take this in groups of 4 and have a break after each one. And I already feel like I need some coffee, but I'm gonna go for it. I'm going to do the first 4 questions, and then I'm going to take a break. Okay, first question, page 238. I love this question, thank you. So the question is GEBEGB a product? And this is the Gödel-Escher-Bach front cover, which is an amazing woodcut that projects G, E, and B in different directions. And thank you so much for this question, because I really enjoyed thinking about it. And I had not thought about it before. So it isn't, I don't think it's a product, because it would be a product of 3 two-dimensional things. So if you take a product of a square, do you like my square? It's good, isn't it? If you take a product of a square and a circle, no, let me start again. If you take a product of a square and a line, then you get a cube or a rectangle, a cuboid, because you move the square along in that line, right? If you take a product of a circle and a line, you get a cylinder, a really good cylinder. If you take a product of a 2-dimensional thing and a 1-dimensional thing, you get a 3-dimensional thing. Okay, I need to pause to think about what I'm saying for a second. Right, so if you take a product of a 2-dimensional thing with a 2-dimensional thing, you should get a 4-dimensional thing. And so if you took a product of the shapes made by G, right, so this is a subset of R2. So it's really 2-dimensional. That's supposed to be a G, it's not a very good G. And then there's E. Right, these are all filled in because they're subsets of R2 and B. So if you haven't looked at the picture of the cover of that book, then this won't make any sense to you, but I urge you to look because it's really beautiful. And so I had a look, I had a little Google about it to see what people are saying. And so one thing you can do, what you're trying to do is you're trying to make a subset of R cubed such that the projection onto R2 in each direction is this subset. And so what you can do is, so these sets are called G, that's a subset of R2, E is also a subset of R2, and B is also a subset of R2, then what we're looking for is a subset of R cubed such that when you project it in each direction, you get G, E, and B. And so what we want is points of R cubed x, y, z, such that when you project onto x, y, that's in G, maybe even maximally, that y, z, or maybe let's say x, z. X, z is in E, and y, z is in B. So it's not a product, because a product would have 6 dimensions to it. But what we're actually going to do for the next chapter is pullback. So I think this is a pullback, which I think is rather interesting, because what we're saying is that there's some overlap, right? It's not any old point of G and any old point of E. It's a point of G and a point of E whose first component is the same. It's just like I was just saying about how we do composition of morphisms. And if we drew this as a universal property, what we would be saying, I think, is that there are these sets G, E, and B, and we want to take points in R cubed. So here are the 3 coordinates of R. And what we're saying is that G has 2 coordinates. So here's its X coordinate and its Y coordinate. And E has 2 coordinates. And we want the first coordinate of E to be the same as the first coordinate of G. So we want this diagram to commute. And then the second coordinate of E wants to be the same as the second coordinate of B. And so we want that diagram to commute. And then the second coordinate of G wants to be the same as the first coordinate of B. So we want this square to commute. And so I think that this is a kind of universal property over this diagram. That is what I think. Now I'm really curious to know if that's how he actually constructed it, but I will move on. So that was the first question. Okay, so now we've got some questions relating to the products on page 239. 239. It's the definition of a product and the factorization. So the first question says, can you give an example of a morphism X to A cross B that does not make both of the triangles commute? Okay, yes, I can. So the question is, if we've got objects A and B, and here's the product A cross B with its projections, the idea is that given any object X and morphisms F and G, there is a unique morphism K making both triangles commute. So the question is, can I give an example of a morphism that does not make both triangles commute? So here's an example. If we take the set A to be the set containing the objects 1 and 2, and the set B is going to be the set containing the objects X and Y. So one possible construction of the product is going to have 1x, 1y, 2x, and 2y as its elements. So any 4 element set will do, but I'll write it like that because then it's more obvious what the projections do. So this projection projects everything onto its first component, and this projection projects everything onto its second component. Now, I only need one object up here, and I can call this object 1x. So going down here, I'm going to define this morphism to take it to 1, and I'm going to define this morphism to take it to x. But here is the morphism K, right? I can decide to send this morphism anywhere. And if I send it to 2y, right? According to this factorization, it ought to go to 1x. But if I send it to 2y, then this left-hand triangle is not going to commute because this element will go to 2y and then it will land on 2, whereas that way around it will go to 1. And if I go this way around, it'll go to y, whereas this way around it'll go to x. So neither of these diagrams commute. In order to make the diagram commute, the only place this thing could have gone was 1x. So now the next question, which is related, says, please give an example of a diagram that looks similar but isn't a product because there is more than one morphism making both triangles commute. Okay, so if you put an extra element into here, then you can have two possible factorizations because things will not be uniquely determined. And so the minimal example, I think, is if you just have a single object here, a single element here, and a single element here, but you have two elements here. Right, the product should just have one element, but if we put two elements here, then if we take any object, a set with any element here, right, this morphism, it just has to go to, there's only one element in this set. So it has to go to the asterisk. And this way around, it has to go to the asterisk. And these are the terminal sets. So in fact, anything will commute going to there. So now look, I can send x to 1 and it'll make this diagram commute, and it'll make that diagram commute. I could also send x to 2, and it would also make both diagrams commute. Now, it's possible that example is too small to be, it's technically a counterexample, but maybe it's too small to be illuminating. So why don't I do this one again? And maybe it'll be a little bit more illuminating. So if we've got 1, 2, and x, y, the product ought to be 1x, 1y, 2x, and 2y. But I am going to throw in another object, and it's going to be called 1 primed x primed. So in this direction, 1 primed is going to go to 1, and x primed is going to go to x. Right, so 1 primed, what x primed is like a rogue extra copy of 1x. So now, no matter what set I have up here, okay, I can have a single element here. If this goes to 1 on that side and to x on this side, then there are two possible things I can do here, right? According to the ordinary product, this factorization should have sent it to 1x, which will send it to 1 and to x. But I've got this rogue extra copy of 1x. So I could now also send it to 1 primed x prime, and it will still make both sides commute. And so this has this rogue extra thing, which is making the product too big, so it's not a product anymore, which gives us somewhere extra we could make a factorization so that both sides commute. Okay, I hope that that makes some sense. And the next question is about the shadows of irregular configurations on page 239. The question says, the shadows are intriguing. I'm trying to imagine how they could make a category and fit the definition of a product. Can you help me visualize in what sense one of the sneaky non-canonical configurations to 2 and 4 would be factorized to the full 2x4 grid? Okay, good. So here is one of the sneaky configurations. Right. And so if you like, what you can do is you can think of this as a product where this set is the elements 1 and 2, and this set is the elements 1, 2, 3, and 4. And so we know that the full product ought to be 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, right? And so then the projections this way go to the set 1, 2, and the projections this way So these ones go to the set 1, 2, 3, 4. So again, I haven't left myself quite enough space, but it's okay because I can move it down. So now in our sneaky configuration, we haven't got all of these things. Oh, go away. We've only got 1, 1, 2, 1, 2, 2, 2, 3, and 2, 4, right? So we've still got projections like this, and the unique factorization is the subset inclusion. So everything goes into its same place. If I were now trying to say, okay, well, why isn't this sneaky thing the product using these two projections? So let me try and come up with some way of explaining that. Let me pause this for a second. Okay, so the point is that this thing isn't big enough to be the product. It doesn't have enough stuff. Whereas in that example above, we had something that was too big. So when you're too big to be the product, what we got was that factorizations weren't unique. When you're too small to be the product, what you get is that factorizations might not exist. So that's the interplay between existence and uniqueness. And so if we take one of the things that's missing, we could do 1, 3. So this is the set containing 1, 3. Of course, that could go anywhere, but as long as we send it to 1 and to 3 over here, then what could the factorization be making both these things commute? We need it to go to some object in here such that its first element is 1 and its second element is 3. But there is no object whose first element is 1 and whose second element is 3. So there is no factorization for this, which shows that that is not the product. Okay, very good. That's 4 questions. I'm going to get some coffee and some chocolate, and then I will be back. Okay, I have coffee, I have chocolate. I'm ready for the next 4 questions, except that I haven't drunk my coffee yet. Page 241 to 2. Could one create a diagram that indicates which morphisms commute? If not, how would one make up for it? So page 241 to 2 is the diagram about building up several diagrams with different parts that commute. So here's the thing. When you're drawing diagrams in category theory, when I'm drawing diagrams, when one is drawing diagrams in category theory, typically one tries to only draw diagrams that commute. Or what you do is you draw a diagram that you think is going to commute, and then you fill it in showing that it does commute. We really try not to draw diagrams that don't commute, or at least we don't leave them there because it's really confusing. At the category theory conference I was at in Belgium this month, there was a very funny talk where someone said, we're category theorists, and so there are several problems with this diagram. One is that it doesn't commute, and another is that all these objects live in different categories. And it was very funny. So there is sometimes a time to do it, but typically we try to just draw diagrams that commute. Why would we draw a diagram that doesn't commute? I suppose you might want to prove a theorem saying this diagram doesn't commute, which might be a little strange. I think that's all I'm going to say about that. Next question. Okay, a couple of questions about the souped up category. Is the morphism between cones in the souped up category a 1-cell or higher dimensional because it's mapping other morphisms from inside the cone? So here's the thing. It doesn't matter. What a morphism is inherently doesn't matter. All that matters is what we're considering it as. And when we're thinking about morphisms between cones, this may well be some object in some other category, but in the souped up category, this is an object and that's it. And so when we're having a morphism between the cones, we're thinking of another cone and that is an object. So the morphism between them is just a morphism. It's nothing higher dimensional whatsoever. It happens to correspond to a commutative diagram in a different category. So this kind of addresses the next question, which is there's a sentence that says a morphism K in the souped up category is a morphism K from X to V in C. Since the morphisms exist in two different contexts with different types of objects, what is the sense in which they are the same? So they're not the same. It's just that one of them is given by the other. And in category theory, we get admittedly a little bit cavalier about saying is that can mean different things. So this morphism K, and we kind of name it K because it comes from a morphism K over here. If we were being extremely precise about type checking, maybe we wouldn't call it K over here because it's not actually the same K. It's the same, it's given by the same K. But it would be extremely tedious if we referred to the morphism in the souped up place and the morphism in the original place by a different name. So very occasionally it can be helpful to do that. And so I suppose when you're starting and you're not familiar, you're not sort of adept at moving backwards and forwards between a souped up category and the original category where it's coming from, you might find that you want to give it a different name. But I would encourage you eventually to be so good at moving between those points of view that you really see those as the same thing. I think this is an example of something I'm often saying, which is that abstract math involves a lot of moving backwards and forwards between two points of view on the same thing and being able to hold them in your head at the same time and think about them both simultaneously and also separately. And it's very interesting to me, honestly, to see questions like this, to remember how much that is a muscle that gets built up by practice, really, and that how important it is as a skill in abstract math that maybe we don't talk about. This whole ability to hold things in our head that are different and the same at the same time. Okay, there's my coffee. And the last question of this 4 is page 244. Why is it again that a map from a finite discrete set into A via the projection from A or via the factorisation isn't surjective? My psychic powers are slightly failing me here as well. Don't know why we're talking about a finite discrete set A. On page 240, first of all, I would not say discrete set because a set is always discrete. It doesn't have any morphisms in it. So on page 244, it only says for any set A, and there's nothing about anything not being surjective. However, if A really were finite, there is no way that a function from a finite set to an infinite set can possibly be surjective, because you just don't have enough elements over here to hit all the elements over there, if that's finite and this one is infinite. So that is the next 4 questions, and I'm going to have another break before doing the next 4 questions. Okay, I have more coffee and more chocolate. On to the next 4 questions. So the next 2 questions are about the bijection between the pair of morphisms in a product. So this is on page 244. Just to make sure I'm understanding correctly, the bijection. Okay, so there's a bijection between pairs of morphisms to the feet and a single morphism to the vertex. So what this is saying is that when you have a product, this was for R cross R, but this works for any product. Right, there's the product R squared, and we're thinking about morphisms from A. So the bijection is between pairs F and G and a single morphism to the vertex. So I should say this a bit more carefully. So this is and morphisms K. So this is a set of functions and this is a set of functions, and there's a bijection between them. the vertex is R squared. But P and Q have nothing to do with this particular bijection. It's between pairs FG and morphisms K. So the next question is related, and it says, regarding this bijective correspondence, first of all, is this true in general for categorical products? Yes, that's part of the definition of categorical products. So what we're saying is that the definition of a categorical product gives us that the morphisms from, if you look at the morphisms from X to A, crossed with the morphisms from X to B, right? So now this has gone a bit meta, because this is a set of morphisms and this is a set of morphisms. So I'm taking a product of sets of morphisms. So an element of this product is a pair, something in here and something in here, right? And that this is in bijection with just single morphisms from X to A cross B. But the bijection is produced via composition with a factorization, which makes it even better. I don't think that's right. It's not with via composition with a factorization. It's via composition with the projections. Maybe that's the source of the confusion. I should write that down as a typo. It's via composition with the projections. So how do you get from FG to K? You compose with the projections. And so this is better than any old bijection, because it's really telling us that it's a very canonical bijection. Now, we haven't got to this yet, but what this is saying is that it's a natural bijection. It's natural in X. And we really haven't got to this yet. But what that then tells us via the Untitled lemma is that the entire bijection is completely determined just by one component. And so eventually one of the things the Untitled lemma says is that if you have a natural transformation like this, it's completely determined by where the identity goes. So what that's telling us is that if you put X equals A cross B and you see where the identity goes, the identity here corresponds to the projections PQ. And so then the entire correspondence is induced by composing with PQ. So I'm just going to make a note of that as something to put in as a correction. Okay, good. So I'll just make one more comment about that, which is to stress that whenever you have something saying, for all, there exists a unique, that is a sign that there's a bijection between something and something else. If it's such that a bunch of things commute, then it's quite likely that there's some kind of natural bijection going on where something is induced by composition with something. And that's what most universal properties do. And when you express universal properties with more profound category theory, you do it like that, using that natural bijection rather than being going in with all these precise diagrams. Because when you've got a bigger or more general diagram, you can't draw the diagram necessarily because it's too big. Okay, good. So I'm glad that we did that. Next question. Can you elaborate on why the factorization K is unique? 244 to 245. So there are two possible answers to this. There's the technical one and the philosophical one. So the technical answer for why it's unique is because we've constructed it like that. We've constructed it so that the product is exactly the right size so that there can only possibly be one factorization, right? And we saw in some of the earlier examples in this video that if the set that we put here were any smaller, then we would risk not having any factorization at all. And if it were any bigger, then we would have too many factorizations. So there's often this trade-off between existence and uniqueness, right? As our potential product, if it's too small, then the factorization doesn't exist. So we put in just enough things so that we can get a factorization. But then we stop, because if we put any more things in, then we wouldn't have a unique factorization anymore. And so the uniqueness, what it's telling us is that this set is just determined by the possibility of mapping to A and B and no extra information other than that. The technical reason that the factorization is unique is, well, it was there on page 245, I think. Possibly not worded in the greatest possible way, so maybe I'll adjust that as well. But the point is that we define something to be I was using different notation, sorry. In that example, it was R and R, but it doesn't really matter what these sets are, but I'll just use the same notation. So that's first projection and that's second projection. And this is F and that's G. And we defined K by K of A is going to be a pair of coordinates in R squared, and it's going to be F of A, G of A. And it's kind of the reason that it's unique is because we're trying to make this commute. And so in order for it to commute, when we do the first projection, this first projection is telling us what the first coordinate has to be. And so the first coordinate has to be F of A, and the second coordinate has to be G of A. And so it's really forced upon us by wanting that to commute. So if we tried to make another one, then we know that by the left-hand triangle commuting, we know that P of K primed of A has to equal F of A. And by the right-hand triangle commuting, Q of K primed of A has to equal G of A. Whoops, that's supposed to be a P. Let me just pause for a second. Okay, so now we're going to look at what the definition of R squared is, right? The definition of R squared is pairs X, Y, such that X and Y are in R. The definition of P of X, Y is X, and Q of X, Y is Y. So what that means is that an element X, Y is P of itself followed by Q of itself, right? So now we can look at this again and say that this means that K primed of A has to equal P of itself followed by Q of itself. But what is P of itself? It's F of A. And what is Q of itself? It's G of A. So it's absolutely forced to be that. Now, I'm not sure if that calculation actually sheds any light on why this thing is unique. So I think this is a technical proof that it's unique, but the reason it's unique is because it's entirely determined by the sort of minimal and canonical way of mapping to those two coordinates. And so the next question is, you mentioned the unique isomorphism between A cross B and B cross A. Does that isomorphism make the notation interchangeable? Or is it a matter of the context being worked in that determines whether the notion is interchangeable? Yeah, that is right. So this is a very subtle point. Thank you for mentioning it. And this is why I tried to make the point about the difference between Cartesian products and products. So if we're talking about Cartesian products, then A cross B really is ordered pairs A, B, where A is in A and B is in B. And B cross A, what's this question saying? Right, the unique isomorphism between them. This is on page 246 to 7. B cross A really is, whoops, really is the ordered pairs the other way around. Oh dear, I'm going too fast for myself. And A is in A. So as sets, these are actually different sets. One of them has A in the first component, and one of them has ordered pairs where A is in the first component, and the other one has B in the first component. So if you're dealing with the elements of the sets, those really are different. Whereas if you're dealing with the sets as objects of a category, the category can't tell these apart. And very importantly, if you write A cross B as a product in a category, this is only even determined up to isomorphism. Products are only determined up to unique isomorphism. So it doesn't even make any sense really to say that A cross B is or is not equal to B cross A, because they're both in a category. These are both only determined up to isomorphism. And because we've only determined it up to isomorphism, they're kind of necessarily the same thing. Once you have picked a particular object to be your particular A cross B, then you can say that there is a unique isomorphism to the one this way around. But until you've picked a scheme for which is going to represent your product A cross B, it doesn't really make any sense to think of these as different in a general category. What's happened here is in the category of sets, we have picked a specific representative of the product A cross B, and we can do that consistently across the entire category because we have this concept of ordered pair. So it is a bit confusing because in a general category, this isn't even pinned down as a single object. It's just a whole load of isomorphic objects. We quite often do category theory where we have to pick specified ones of these, in which case we then have a canonical isomorphism between the specified other one. But until we've done that, yeah, we can't say that there's any difference between them. Okay, that question was very deep. And that's the end of that 4. And now I'm going to have another break. See you in a moment. Okay, I'm back. Onward. I've tied my hair back. I've eaten some raspberries. I apologize if I've got raspberry pips in my teeth. The next question is, you write that Cartesian products are just one particular construction of categorical products in set. Can you give examples of non-Cartesian categorical products in set? Well, here's the thing, that in set, all sets of the same cardinality are isomorphic. So if I go back to that example that I constructed up there of the Cartesian product of 2 things and 2 things, where's it gone? There it is. This, if I just get rid of the stuff that wasn't part of the product, so this is not supposed to be there. So this product is the product of this, is the Cartesian product of this set and this set. But anything that's isomorphic to it will also be a product. So I could just as well, well, not just as well, but I could hilariously make a product, a categorical product of these 2 sets that consisted of the set A, B, C, elephant. Now I have to make projections. So I can, as long as I declare that this is, do this right, then it'll make a product. So what I need to do is kind of pretend that these were really 1x, 1y, 2x, and 2y, because what I'm really doing is making an isomorphism with that. So if I pretend that secretly that was actually 1x, this is 1y, this is 2x, and this is 2y, then what I'm saying is that P of A is 1. So P, we've got A, B, C, elephant. and it's going to go to, A is going to go to 1, B is going to go to 1, C is going to go to 2, and elephant is going to go to 2. And then for Q, we've got A, B, C, elephant. And it's going to be that Q sends it sends A to X, B to Y, C to X, and then elephant to Y. And this diagram is now a categorical product. So if I take any set X up here, together with morphisms F and G, then how do I make the factorization? Well, I look at where an element X goes. So I'm trying to construct a factorization K. So K of X, well, you have to look at where it goes under F. So if it goes, wherever it goes under F, it's a bit harder to express now, but wherever it goes under F, supposing it goes to 1 under F and it goes to X under G, then I've got to find the thing that goes to 1 under X and also goes to 1 under P and X under Q. So that would be A. Okay, so if you wanted to make a systematic scheme for doing this, what you could do is you could make a grid and say, okay, look, I want to decide which elements correspond to which. So here are the things that go to 1 and 2. Here are the things that go to X and Y. Okay, who goes to 1 and X? Well, that's A. Who goes to 1 and Y? Well, that's B. Who goes to 2 and X? Well, that's C. And who goes to 2 and Y? Well, that's elephant. And now this grid will help me systematically decide where K goes, because I look at the element X and I see where it goes under F, see where it goes under G, find the corresponding spot in here, and that's where K sends it. But oh, look, what have I actually done? What's this grid doing? This grid is actually making a bijection between this and the Cartesian product. And so that's why any bijection between this and the Cartesian product amounts to giving it the structure of a product using with projections. So this is an example of a categorical product that is not a Cartesian product. Okay. Page 251. In the bottom diagram, for this factorization, I'm wondering if the outer morphisms could be labeled 10 and 15. They could be, as long as you're clear what you're doing, that's dividing. You can label them whatever you want. So then the next question is, could you help me understand why the 6 and 10 examples are a cone and not a product? On page 252, I think they are a product. It says, let's now look at the categorical product of 6 and 10. I'm wondering if you mean to help you understand why you don't get, why the categorical product doesn't give you the actual product. Because 6 and 10, the actual product of numbers is 60. But that's not the categorical product. And one way you can see it's not the categorical product is that 30 perfectly well has, if we were doing multiples, and as in the previous question, we could label these by what the multiple is. So this is via a multiple of 5, and this is via a multiple of 3. But there isn't a morphism, there isn't a factorization, womp womp, because 30 is not a multiple of 60. And so that's why the product is the lowest common multiple and not the product of numbers. So then the next question says, could you explain further the lowest common multiple definition used in abstract mathematics? I'm not sure if I can, because I think I put all the explanation that I have in there. So let's see, what did I say on page 253? Oh, maybe I can. So you might say that you might think that the lowest common multiple is the lowest among all common multiples. So if you were going to define it as that, you might think it means 1. So it is a number m such that 1, m is a multiple of A and B, and 2, if X is a multiple of A and B, then, well, M is supposed to be the lowest one. So that means that M has to be less than or equal to X. And that's probably the kind of definition that comes up in school, middle school or high school, when you first do lowest common multiples. However, this definition is a bit unsatisfactory in abstract mathematics because we're looking at two relationships between things. We're looking at multiples and we're looking at less than or equal to. So abstractly, it's more satisfactory to replace this one by a multiple definition as well. And so we instead say that if X is a multiple of both A and B, then X is a multiple of M. And those definitions turn out to be equivalent because if X is a multiple of A and B and it's also greater than or equal to M, then it can't just be greater than or equal to by some random amount. It has to be a multiple. This is also more abstractly satisfying because it means that it's the categorical product inside the poset. So I hope that helps with that. That's the next batch of questions, and I'm going to take another break now. Okay, am I recording? Am I recording? Yes, I am recording. Next 4 questions. Just making sure I understand. The vertex of a product in a poset is the least upper bound, if it exists. Yes. So categories don't necessarily have products, and posets don't necessarily have least upper bounds. Do you know why the least upper bound is called the supremum? Well, I Googled it, and I don't know how deep your question is, but it comes from the Latin, super meaning over. Why somebody decided to do it like that, I don't know necessarily. There's a little bit of grammar involved. Super means over, supremus is the superlative. I suppose it means best. It's like it is the most upper, the best of the upper. So I suppose you might wonder, I don't know what the nature of this question is, whether it's about why it's called why it's used for the least upper bound and not the sort of most upper bound, but it's the best upper bound. So the next question is the coproduct the universal cocone only in C-op? I don't think so. I think it's the universal cocone in C or the universal cone in C-op. So a universal cone in C, ooh, I'm red. Let's do that again. A universal cone in C is something that looks like this with a universal property. A universal cocone, so this is a cone, and this is a cocone. A universal cocone is something that looks like this with a universal property. So this is a cone in C, and this is a cocone in C. A cocone in C is a cone in C-op. So the coproduct is not a universal cocone in C-op, it's a universal cone in C-op. The next question is page 262, and it says, why does being unique up to isomorphism make cocones commute? And I think that this is my sentence wasn't very clear. So it says at the bottom of page 262, so coproducts are unique up to unique isomorphism, making cocones commute. So it doesn't, it's not that unique up to unique isomorphism makes cocones commute, it's that it's only unique up to unique isomorphism making the cocones commute. So this is all about dual versions of everything that are true for products. So all I'm saying, I'm listing the things that we know are true for products, and I'm saying that we know them automatically, instantly, by duality for coproducts. And so the next part of this question is, what do you mean when you say there are n-fold versions? So if you look back to where I did this for products, this is on page, okay, I found it. It's at the bottom of page 250. There is a threefold product that is not derived from binary products. And then at the top of page 251, it says, try investigating the categorical threefold product. And then in terminology, it says, if a category has binary products, then by induction, we can build up to n-fold products for any n. So we can say the category has finite products. And so for products, we've had the binary product, which is a cone, a universal cone like this. And then we can have an n-fold product, which is a universal cone to n objects. So the coproduct case, we had a binary coproduct, where we just turn the arrows around. And so then a n-fold coproduct would be where we have n objects and we have insertions like that. So this would be like in set, it's the disjoint union of two sets, and here it's the disjoint union of n sets. Okay, that takes us to the next 4 questions, and I will take another break. All right, here we are, last 4. Can you explain in a little more detail the footnotes? So there are several questions about this, the footnotes on page 254 and 266 about the abstract explanation of the optimistic method. What do you mean by cocones are harder to construct for sets of algebraic structure? Why are co-limits harder to construct? What's the more abstract explanation in terms of algebras for monads? And what's the difference between an algebra and a monad? So the reason that I put this in a footnote is so that if you heard of things like algebras and monads, you can look it up if you want to. And so if you don't know about algebras and monads, then this bit won't mean very much to you, but I'll address the questions anyway because they're there. So monads are a way of expressing algebraic structure. If you want to know more about them, then there's always my first ever YouTube video, Monads 1 from the Catsters in 2007. A monad is it's a functor, and it's a functor on an underlying category that kind of generates stuff. And in terms of algebra, you can make it generate the stuff that you need for your algebraic structure to be there. So a set with a structure can be expressed as a set, and then you have this monad, which is a functor from set to set, satisfying with certain conditions on it. And so you generate all of the structure that you need, and then you find a place for it in A. So this is an algebra for a monad. There are a lot of other axioms that I'm not talking about. And so, for example, for a monoid, this is A can be the underlying set of the monoid, and then TA is all the things that you need in the monoid. So you need binary products, and then you need binary products of binary products, and so on. So you end up with words of elements of A up here, and then you evaluate them. So this map is the algebra structure that evaluates all those things in A. So the monad is like the theory of monoids, and the algebra is like an actual individual monoid. So in the theory of monoids, you go, well, in theory, a monoid needs to have this, and a monoid needs to have this. And then you go, okay, in this particular monoid, this particular monoid has this particular structure. So there are various theorems about categories of algebras for monads. And one is that if you have a monad T on C, then the algebras for it, which I'll write like this, the category of algebras lives over the category C, because an algebra for T has an underlying object in C. So there's a forgetful functor back to C. So this is like the forgetful functor from monoids to sets, where you forget the monoid structure. And there is a left adjoint. So we don't know about adjunctions yet. This is why this is all lots of things that we don't know about, but I'm including this because people did ask. So what you have is you have a forgetful functor, and you have a left adjoint, which is the free functor. And the free functor takes an underlying object and generates an algebra freely. And one thing that's true about adjunctions is that any functor that has a left adjoint preserves limits. So that means that if something is a limit in here, then when you do the forgetful functor on it, it has to still be the limit here, which means that if you're looking for products of algebras, you can simply say, well, once I apply the forgetful functor to them, it has to be the product down here. So I know that the underlying object of the product up here, if it exists, must be the product of the objects down here. So when you take the product of monoids, you know that the underlying object needs to be the product of the sets. However, when you're doing coproducts, you don't get to do that, because this right adjoint doesn't preserve colimits, it preserves limits. This left adjoint preserves colimits. Let me just pause for a second. Okay, so what I was saying is that this left adjoint preserves colimits, which means that if you start with a colimit down here and you apply this functor, you get a colimit up here of the free things. Did I say that right? That was the whole reason I paused the video, was to check if I was saying that right. And now that it's started again, I need to think about it. So that would say, for example, that if you have a coproduct A plus B down here, nope, I need to pause the video again. Gosh, it's funny how that happens. Okay, let me actually draw it out. It's funny how easy it is to get a blank when you're trying to explain things to people. And I think it's because if you're trying to explain something to someone, you're trying to empathize with another person. Whereas when you're trying to, the thing that you're trying to do technically uses a different part of the brain. It's really difficult to access both parts at the same time. So preserving coproducts means that if you start with a coproduct over here and apply F to the entire diagram, is it still a coproduct? And so if it were still a coproduct, what we're trying to say is it the coproduct of FA and FB? So the fact that this preserves coproducts gives us a way, colimits, gives us a way of taking colimits of free things. It doesn't give us a way of taking colimits of things that aren't free. And so in general, that's why things like taking a coproduct, a colimit of monoids is much more complicated than taking a product of them. For a product of them, you just, if you want to do, if A and B are monoids and you want to take a product of them, you just say, okay, well, what is the product of the underlying sets? That will be the underlying set of the monoid. So it's going to be ordered pairs, and then we do the algebra structure in each component. Whereas to take a coproduct of monoids is much harder, because the underlying set will not just be the disjoint union of the underlying sets, because the binary operation up there means that you now need to make a binary operation involving an element of A and an element of B. And if you just take the disjoint union of the underlying sets, the A's and the B's will never be interacting with each other. And so we need things like AB, which is not in this disjoint union. And so that's why taking coproducts, colimits, is harder. There are, however, theorems about how you take the colimits in certain situations if you really do have this kind of adjunction going on. So that is what the that is what the optimistic method and what the footnote is about. That was quite advanced, so I hope that just gave you an idea without being too off-putting if that was much beyond you. So we have done it. We've made it to the end of our 28 questions, and I am quite exhausted, and I'm very impressed that there were so many questions. So thank you very much for that. I'm glad that I didn't try and do this. I know it's a bit late in the 2 weeks, but I'm glad I didn't try and do it earlier, because there were a lot of days when I had just about 2 hours or maybe an hour and 45 minutes to do it. And I thought, I just don't know if it's going to fit. And I kept looking at the list of questions thinking, I don't think I can do this in that time. And it's funny, after a while teaching and making videos, you can look at some material and kind of know how long it's going to take without having to try it out. And I just kept looking at it thinking, no, I just don't think I can do it in 2 hours. And indeed, I did not do it in 2 hours. Maybe the video will turn out to be 2 hours. I'll be quite interested to see, but it has taken me 2 hours and 15 minutes together with 45 minutes of thinking time at the beginning. So, gosh, I hope I'm recording. I am recording. So finally, praise. Going through this book is very therapeutic. Thank you. Oh, that's nice. And maybe I'll stop the share so that there's more video going on. Stop share. Thank you so much, Eugenia. Well, thank you. Thank you for your patience. Well, thank you for your questions. Thank you for being a maths speak mythbuster. That's quite a tongue twister. I really appreciate that you're the kind of mathematician who sees mathematical concepts and analogies in the real world as well. Oh, thank you. Yeah, I do. The first time I encountered category theory, I thought I'd been thrown onto a different planet. I mean, that's kind of fair. Your book has helped me to realize it may be a different country, but it's not so intangibly distant. Well, that's interesting, because things get closer the more that you understand them, right? It's like going to a foreign country, that it can feel like home after a while. Thank you so much. Thank you to the people at the Topos Institute and Dr. Cheng for continuing the book club. Thank you. And thank you so much for trying to create general answers to questions that are challenging to pin down. Yeah, it's quite challenging sometimes. I appreciate the work involved in trying to collate all our questions into something useful for the book club. Thank you. Well, thank you, everybody. And thank you to everyone at the Topos Institute for helping us with this. Next, we'll do chapter 19. It's very exciting. We're really getting into this stuff now. So well done, everyone, for being here. Thanks for being here, and see you next time. Bye.